Bom, boa noite, good night for everyone, boa noite a todos. Vamos dar início aqui ao nosso webinar, só para vocês ficarem sabendo, gente, esse webinar está sendo gravado, porque a gente pretende utilizar esse webinar depois, tá? Bom, esse webinar nós preparamos para a gente poder falar sobre o título dele, né? Sólidos e cristalização. Nós vamos abordar sólidos e cristalização. Então, o objetivo desse webinar é falar sobre atributos de qualidade, estado sólido e também cristalização. Eu sou Maria Clara Ramalho Freitas, prazer, para quem não me conhece. Eu trabalho na Solid Cunsult, empresa de consultoria da Indústria farmacêutica e farmacêutica. Nós oferecemos serviços de consultoria, também cursos e treinamentos e desenvolvemos também um produto de inovação. Estou aqui com o meu parceiro para esse webinar, o Moussa, Boukerche, que vai falar sobre cristalização para vocês. Então, eu vou começar falando sobre atributos de qualidade de estado sólido e, na sequência, ele vai abordar a parte de cristalização. Então, o objetivo é falar sobre esses tópicos e também fazer uma oferta para vocês. Nosso objetivo é trazer aqui um curso, também de mesmo nome do webinar, Sólidos e Cristalização na Indústria Química e Farmacêutica. E hoje, para vocês que se comprometeram a estar aqui no webinar, nós vamos oferecer esse curso com mais de 50% de desconto. Foi até interessante, se vocês procurarem na internet, tem o mesmo curso disponível, só que na França, e ele está por um valor em torno de 2.500 euros. Aqui, né, nós estamos no Brasil, a gente vai ofertar esse curso por 2.300, mas hoje a gente vai ofertar ele para vocês com mais de 50% de desconto. E para quem que é esse webinar, tá? Eu acho que é importante a gente ter clareza no objetivo e para quem que é. Esse webinar é para quem trabalha na indústria química e farmacêutica, na parte de farmacotécnico, pré-formulação, controle de qualidade, regulatório. Também o pessoal que trabalha com a parte de processo, né, sendo os químicos, os engenheiros químicos, mas não somente para a indústria química e farmacêutica, mas também para quem trabalha na indústria de cosméticos, na indústria alimentícia e na indústria agroquímica. Porque tanto atributos de qualidade de estado sólido quanto a parte de cristalização, elas são extremamente importantes para todas essas indústrias. E de quem que vocês estão vendo? Essa parte inicial, né, o ponto de vista que vocês vão ver, os atributos de qualidade de estado sólido, vocês vão ver do ponto de vista de mim, né, Maria Clara. Eu tenho formação acadêmica, eu me formei em Química pela Universidade Federal de Juiz de Fora, também mesma universidade onde eu fiz mestrado. Tive a oportunidade de fazer um estágio na universidade, Pontifícia Universidade Católica do Rio de Janeiro, durante meu mestrado. Quando eu terminei meu mestrado, eu fui fazer meu doutorado na Universidade Federal Fluminense. Também tive a oportunidade de fazer um estágio na Universidade de Berna, na Suíça, durante meu doutorado. Quando eu retornei, defendi, eu já tive a oportunidade de ser gerente de laboratório de extração de raio-x. Nesse laboratório, eu tive a possibilidade de fazer vários projetos em colaboração com os pesquisadores do estado do Rio de Janeiro. E no mesmo período, eu também tive a oportunidade de ser professora substituta na Universidade Federal Fluminense, no Departamento de Química, enquanto eu fazia o gerenciamento do laboratório no Departamento de Física. Depois de 2 anos, eu passei como efetiva para professora efetiva na Universidade Federal Rural do Rio de Janeiro, Departamento de Química. E depois desse período de 3 anos, eu saí da universidade e fundei a Solid Cunsult, empresa de consultoria. E aqui, tá, ainda trazendo clareza sobre esse seminário, eu gosto de mostrar, perguntar para o pessoal, para eles se situarem onde a gente está, né, vocês estão, com relação ao conhecimento. E aqui nós temos um gráfico que mostra os desafios em função da habilidade, né? E aí nós podemos estar em vários pontos em relação a esse, quando a gente avalia o nosso conhecimento tanto sobre cristalização quanto atributos de qualidade de estado sólido. Se a gente tem um desafio muito alto e poucas habilidades, vai gerar na gente um estado de ansiedade. Não é isso que a gente está buscando, a gente está sempre procurando ter altos desafios e também uma habilidade técnica para enfrentar esses desafios. Então, quando a gente está com habilidades, né? Conhecimento suficiente para enfrentar os desafios, a gente consegue fluir melhor no nosso serviço. E é isso que a gente está propondo aqui para vocês, que a gente possa aumentar a qualidade técnica dos nossos conhecimentos e também os conhecimentos acadêmicos e também práticos, já uma vez que o Moussa ele tem experiência na indústria farmacêutica, ele pode compartilhar muito do conhecimento dele. E eu, bastante, com a parte de conhecimento da parte de pesquisa, devido à minha formação acadêmica. Então, quando eu falo de atributos de qualidade de estado sólido, estou falando, me referindo a 3 atributos, tá? Que seriam eles, né? Quais atributos são esses? Polimorfismo, hábito cristalino e tamanho de partícula. Então, o que seria o tamanho de partícula? Quando a gente fala de tamanho de partícula, né, nós não estamos nos referindo a um tamanho, uma vez que a gente busca, assim, a homogeneidade da amostra, mas a gente sabe que a gente não tem apenas um tamanho de partícula, nós temos o que a gente chama de distribuição do tamanho de partícula. Essa distribuição, então, ela vai seguir, né, uma curva de uma gaussiana, e aí quando a gente vai falar do tamanho de partícula, nós nos referimos a D10, D50 e D90. E o ideal é que essa curva seja uma gaussiana, que ela apresente apenas um nó. Não é o que a gente observa algumas vezes, né? Às vezes essas curvas são binodais, mas isso também a gente aprende também com a prática, mas tamanho de partícula, então a gente faz as análise de tamanho de partícula e busca informação sobre D10, D50 e D90. Quando a gente fala agora de hábito cristalino, também um outro atributo de qualidade de estado sólido, nós estamos falando da face externa desse cristal. Geralmente, tá, essa face externa pode ser ou não uma consequência do arranjo interno. Mas essa face externa, ela também é um atributo de qualidade de estado sólido, assim como o tamanho de partícula. E, por último, o polimorfismo. O que é esse polimorfismo? Ele é consequência do arranjo interno do material. Então, como as moléculas se empacotam, pode gerar ou não estruturas polimórficas. Quando eu falo de estruturas polimórficas, tá? Poli vem de vários e forma várias formas. Então, pode ser que para o mesmo conjunto de moléculas, né, para o mesmo insumo farmacêutico ativo, a gente possa ter ele em vários empacotamentos gerados por condições sintéticas, condições da cristalização. E aí, quando eu falo, né, de polimorfismo, eu uso muito aqui o que a gente chama de analogia da parede. Então, eu utilizo, imaginem que nós temos tijolos e a gente vai empacotar esses tijolos, e esses tijolos, ao serem empacotados por pessoas diferentes, não necessariamente eles vão ter o mesmo arranjo. É o que pode acontecer, por exemplo, no nosso sistema sintético, se a gente não tem um controle fino, um ajuste fino das propriedades sintéticas. Por exemplo, se a gente altera o solvente, a gente pode levar à formação desses estruturas polimórficas, ou seja, é como se o arranjo, se as moléculas se empacotassem em formas distintas, mas não somente pelo solvente, tá? A gente pode ser que às vezes a gente use o mesmo solvente e condições como temperatura, uso de sementes, isso também Moussa aborda também. Durante o processo de cristalização pode levar a essas estruturas polimórficas. Então, são esses 3 atributos. Por que eles são atributos de qualidade, tá? Quando a gente está falando de medicamento, a gente busca qualidade, eficácia e do medicamento, né? Então, a gente tem que garantir essa qualidade de medicamento. Como que a gente faz isso? Tendo certeza sobre esses atributos. Se esses atributos eles variam, eles podem alterar as propriedades físico-químicas, influenciando, por exemplo, os atributos de qualidade da matéria, como estabilidade, solubilidade, biodisponibilidade. Ou então, nos atributos do processo, eles podem influenciar, por exemplo, no fluxo, na compactabilidade e também na compressibilidade. Então, isso, se influenciar na matéria ou no processo, vai ser um parâmetro crítico a ser avaliado, né? Critical Material parameters ou critical process parameters, tá? São esses dois, essas duas influências, tanto na matéria quanto no processo. E aí eu trouxe aqui um exemplo para vocês entenderem a importância desses atributos, tá? Então, quando a gente está falando de atributos de qualidade, eu trouxe um exemplo prático que é justamente quando um dos parâmetros está influenciando sobre o processo. Que a gente já falou bastante aqui na Solid Cunsult, nós já falamos bastante sobre a questão de... Era Cristo sobre os, tá, gente? Por isso que está o logo antigo. A gente já abordou bastante aqui a questão de alterar as propriedades da matéria, mas eu quis trazer um do processo para conectar com a parte de cristalização. Então, esse artigo ele é bem interessante, ele se chama Downstream Traceability of Crystal Active Modified Active Pharmaceutical Ingredients. E aí, nesse caso, o que acontece? Eles avaliaram como que o processo de cristalização podia influenciar o hábito cristalino e a alteração desse hábito cristalino podia levar a parâmetros, a alteração dos parâmetros do processo, tá? Como, por exemplo, fluxo, ângulo de atrito. E aí, nesse caso, o que eles fizeram? O que eles conseguiram, né? Para uma mesma forma polimórfica, 6 distintos hábitos cristalinos. Como vocês podem ver aqui, ó, eles obtiveram, né, hábito cristalino no tipo de barra retangular, ou então no formato de placas, agulhas, né, needles, que chama, de uma forma de esferoides, romboédrica, ou então hexágonos elongados, como vocês podem ver aqui pela figura de microscopia eletrônica de varredura. E aí, por essa figura de microscopia eletrônica de varredura, a gente pode, é bem claro que esses hábitos cristalinos, essas faces externas do cristal, elas são distintas. E aí, o que eles fizeram? Que eu achei... Por que eu uso muito esse artigo? Porque ele foi muito didático na escolha dele. Então, por uma mesma forma polimórfica, eles alteraram o hábito cristalino e aí avaliaram quais eram os parâmetros do processo que eram melhores ou piores para os diferentes hábitos cristalinos. Eles utilizaram um gráfico de teia de aranha para poder fazer essa avaliação. Então, aqui, como vocês podem ver, nós temos razão do fluxo, né? Esse ângulo efetivo de fricção interna, a densidade, também a resistência à tensão. Então, o que eles fizeram? Eles avaliaram esses parâmetros para os diferentes hábitos cristalinos, para poder dizer se esse hábito cristalino ele era efetivamente funcional, se ele era benéfico para o processo, né, para o processo downstream ou não. E aí, nesse gráfico, eu achei fácil, porque assim, quando você encontra um hábito cristalino que tem, né, o maior valor, ou seja, de 0 até o maior valor aqui nesse vértice desse gráfico de teia de aranha, o maior valor seria aquele cristal, aquele hábito cristalino que tem uma melhor propriedade. Menos aqui, tá, gente, para o ângulo efetivo de fricção interna, porque esse, quanto maior o valor, quer dizer que pior é a questão para a processabilidade desse hábito cristalino. E aí, nesse caso, como vocês podem ver, eles puderam comparar diretamente esses diferentes hábitos cristalinos. E por que eu estou trazendo esse exemplo aqui, tá? Porque muitas vezes, quando a gente quer melhorar, né, o processo, fluxo, a razão do fluxo, ou então a tensão, né, em função da compressão, muitas vezes o pessoal pensa, é uma estratégia alterar o tamanho de partícula, mas ao invés de alterar o tamanho de partícula, pode também pensar em alterar o hábito cristalino. Então, por isso que eu trouxe esse exemplo aqui, que eu acho que é importante, talvez possa trazer uma alternativa em relação a alterar o tamanho de partícula durante o processo de obtenção do material sólido. Bom, o que eu tinha para apresentar para vocês era isso, e eu espero que vocês tenham ficado convencidos sobre a importância de entender sobre os atributos, qualidade, estado sólido. Amanhã nós vamos voltar com mais exemplos. E agora eu vou pedir ao Moussa, Boukerche, para continuar com a parte de cristalização. Moussa? Can you?
Yes, I kind of understood that you were introducing me for the next stage. So, boa noite to todos, and desculpa, no falas português yet, but so my talk will be in English, and I need to put my glasses on as well because I'm a bit old now. All right, so Maria, I'm going to share my slides. That's
Yes,
okay with you?
please.
Okay. So I will try to do that in half an hour or less than half an hour. So we have like 5 minutes at the end, like to answer any questions the attendants may have. Can you see my slides?
Yes, I can.
Okay. All right. So boa noite a todos. My name is Moussa Boukerche, and I'm very pleased to join forces with Solid Cunsult Pharma, so with Maria, for this first part of this webinar. And the ultimate goal of this webinar from today and tomorrow is first to get to know each other and also to introduce you to the course that we're going to give in October called Controlled Crystallization Training Course. So my background is 25 years of experience in the field of crystallization process development. I worked in 4 different countries and in 5 different industries as well, mainly pharmaceutical industry, but also high tonnage, not fine chemicals, but large chemicals. So the outline of my talk today, so as I said, it's a 2-part. So we have today, 27th, and we have another part tomorrow. So for today, I'm just going to start by introducing myself and in fact, walk you through my experience in terms of crystallization, starting from my hometown, from Clermont-Ferrand in middle of France. And then after, the second part of the talk will be about everyday life crystals. So crystals are everywhere, crystallization is everywhere. And I just want to give you some general knowledge and culture around crystallization and crystals in general. And I will finish that part of the talk by just describing and detailing the part 1 and the part 2 of the course that we're going to be giving in October. So tomorrow we will have another part where we're going to talk about the role, which is going to be more detailed in terms of and more focused on the pharmaceutical industry, which is most of my experience. And we're going to talk about the role of a crystallization scientist in the industry, in the pharma industry, but not only in the pharma industry, because crystallization and the fundamentals behind crystallization can be applicable to a lot of different industry. I understood that Maria was talking about agrochemistry, cosmetic, food industry, fine chemicals like polymers, etc., as well as large molecules like peptides, polymers, etc. And we will talk about why physical property matters and how we control them, and the opportunities for particle engineering. So I will give you a real-life experience or real-life case study where we had to change the morphology, and that's exactly what Maria was explaining just earlier on, where we had to change the morphology in order to fit the drug product CQAs. As I said, eventually, these talks and these webinars are leading to that online course that will start in October. So my understanding is Maria will do the solid form on the Tuesdays, and I will do the crystallization process development on Thursdays, and it will start from October 5th. And it's going to be a 4 times 3-hour course session, so 3 hours per week until the end of the month of October. So without further ado, let's get started. Let's talk about me. So my name is Moussa Boukerche. I'm French. I was born in Clermont-Ferrand. So I'm married with Hannah, who is British. And I have 2 boys, Oscar and Arthur, who are 9 and 7. And they were born in Indianapolis in the US. So with this talk, you will understand how I come from and where they come from as well. So I was born in Clermont-Ferrand, as I said, like it's in the middle of France, south of Paris and west of Lyon. That's a place which is covered with volcanoes. That's the longest chain of volcanoes in Europe, I guess. Dead volcanoes, or in fact, they are asleep. That's where the Volvic water is coming from. I'm not sure if you have Volvic in Brazil, but you don't know this one, all right? Fair enough. So Volvic, it's very famous water. You can find some in the US as well, where I was living. And in fact, it's coming from those volcanoes, and those volcanoes have the particularity of making some basalt, which is a dark rock. And with this dark rock, back in the days, in the 11th century, they built this big cathedral in Clermont-Ferrand. And its particularity is like it's a black cathedral because it's made with the Volvic stone, which is the basalt. So so it's a place full of history. And from this cathedral, Urban II was the Pope in the 11th century, ordered the first crusade in the Middle East in order to get back the Saint Sepulchre, which is the tomb of the Christ, from the Arabs and the Muslims there. It was in 1095. So it's also a place where Blaise Pascal, so maybe you are more aware of Blaise Pascal, was a French mathematician, inventor. So what we call a genius, but with the French sense of it. When I was living in the US, everybody is a genius. As long as you do something a bit interesting, you're a genius. But this guy was a polymath, someone who was like a scientist, an inventor, a philosopher, etc., etc. And he was the first one as well, or maybe not the first one, but this tool here that he has invented, it's called the Pascaline. And it was the first, not the first, but one of the first AI in the sense of augmented intelligence, because that was the first calculator. And he invented that, in fact, to help his father, who was a tax collector, and he needed to have a way to make calculation faster. So as we have AI today to get things faster, that's what he did. You might know him as well if you've done some NMR. If you are an organic chemist and you did some NMR, you might be aware of the triangle of Pascal. That is also used to explain the combination between atoms altogether and how they vibrate and give that signal in triplets, singulets, multiplets, etc. in the NMR signal. Clermont-Ferrand is also the home of Michelin, the Michelin tires. So maybe you know. So I show you here like the evolution of their logo. You can see the first one here. Can you see my yeah, you can see it. So that first one here looks like a little bit like a mummy from Egypt. Bit interesting, but just to tell you, like they started in 1898, and in fact they have a good connection with Brazil, because I remember when I was a kid, I had a friend, his father used to go to Brazil quite often, and he was working for Michelin, and I was wondering why. And the reality is because Michelin used to be sourced with their rubber from Brazil, because that's where it's called the Hevea brasilensis. So that's the tree that gives the rubber that was used, in fact, to make tires. Right. So from Clermont-Ferrand, so I stayed there until I was 20 years old, and then I moved to Marseille. And I went to the ENSPICAM, which is the, so it's French this time, École Nationale Supérieure de Synthèse de Procédés d'Ingénierie Chimique d'Aix-Marseille, which means basically Superior National School of Synthesis, Chemical Engineering of Aix-Marseille. I'm a French engineer. So engineer in French is not the same as engineer, exactly like in the US. Ingénieur in French comes from the word genius, like Blaise Pascal, whereas engineer in English is coming from the engine. So from the revolution, the industrial revolution. So it's not exactly, although we use the same term, more or less. So now it's called as the École Centrale de Marseille. And there I was doing like some, obviously, chemical engineering, but also organic chemistry. And at that time, I had a lot of problems because we used to do, like every Thursday, for instance, we used to do practical skills in the lab as a student, where we would learn how to synthesize molecules. And all the organic steps were very well detailed. You do that, you add this reactant, you wait, you agitate, this and that. And then the last step was the crystallization. But the crystallization was always like a bit weird. And in the sense that, for instance, I would, and what we've been told to do is like basically you dissolve your product in a minimum of solvent, you heat up, and then you cool down, and then you'll get some crystals. But sometimes I would have crystals and my friend wouldn't have any, or the opposite, or they would have a lot of crystals and I would have like just few of them. They would have like needle-like crystals and I would have different type of crystals. And I used to ask my organic chemist teacher, how is it, why is it that, why this happened? And most of the time I couldn't have any answer from those guys who were like researchers and were experts in their field of organic chemistry, but they had no idea about crystallization phenomenon. So at that time, I thought that crystallization was an art much more than a science. So I went to Lyon. So I did a little bit of research about crystallization, and I found like a lab in Lyon, which is called the LAGEP, the Laboratoire d'Automatique et de Génie des Procédés, so Chemical Engineering and Automatic Laboratory. And I did an internship, and I applied for an internship in Lyon with Professor Jean-Paul Klein. Jean-Paul Klein was a big name in the crystallization, process development, and industrial crystallization. He was responsible for all the sites for Ron Poulenc across Europe for crystallization, filtration, and drying. And then after a career in the industry, he moved away and went to the academic world, where he built the Institute of Technology of Chemical Engineering of Lyon. And he's the one who built that. And obviously, he kept doing like some research in the field of crystallization, and he had like tons and tons, a lot of PhD students along the years. So when I went there, I met with Dr. Sergio Martins, who is Brazilian as well. And he was coming from Ron Poulenc, but from Brazil. And he was sent in France in order to learn about crystallization. So he went to two places, Marseille, where he worked like at the CINAM, and I will give you a description of this lab, where they look at much more fundamentals about crystallization, crystal growth, etc. And part of his assignment as well was to spend like some time in Lyon with Professor Jean-Paul Klein to then understand, based on the knowledge he got like from Marseille about fundamentals of crystallization, nucleation, crystal growth, etc., use that knowledge for industrial crystallization. So the purpose of my internship was, can we determine the kinetic of a crystal population, so particle size distribution, so the entire population, based on the kinetic of just the faces of a single crystal. So basically, the idea was we just use like one single crystal, we measure the speed at which those faces are growing, right? Determine their kinetics and use those kinetics, in fact, to do some modeling on the entire population of crystals. And in fact, what we have realized after this work is that, akin to the sociology field, so the human life, we cannot predict the behavior of an entire population solely based on the observation of a single individual. And that's true as well for human. You cannot tell that all Brazilians are like Maria or all French are like Moussa, right? You have to study the entire population. And that was the outcome of that discussion. But what I understand the most is like crystallization is a science. And that's where I've started to learn about how to deal and control about crystallization scientists, about crystallization science in general. And it's a science that is gathering a lot of different topics, like from organic to inorganic chemistry, thermodynamic, kinetics, as well as hydrodynamic. And hydrodynamic is very important when you're starting to deal with scale up. And we'll get to that a little bit further later. So I spent a lot of very good time with Sergio Martins, who is like still working at Solvay. In fact, Ron Poulenc is becoming Solvay and is still located in Brazil. So if I have the chance to come to Brazil, I will go and visit him as well. And we used to talk a lot about science, but more importantly, if you can see here, it was 1998. So I'm not sure if most of you were born at that time, but that was the time where, sorry guys, we won the World Cup against Brazil in final. So we spent a lot of time talking about crystallization, but a little bit about about football as well. And he was very upset. It was 2 months. I met him 2 months after the final, but he was better, but he was still upset. Anyway, let's move on. So in terms of science, what did I learn? Is that, in fact, if you want to control crystallization, you need to have a map. And your map is your phase diagram. The phase diagram is composed of mainly the solubility. So here, that's the red curve that you can see here. That's what we call a direct solubility. So it means that the concentration is increasing as the temperature is increasing as well. So I must say first that the solubility is a thermodynamic equilibrium. That is the maximum of solute. Solute is the molecule which is in the solvent, which is dissolved. So that's the maximum of solute that you can dissolve at a given temperature and a given pressure. So as I say, in this case here, it's a solubility which is increasing with temperature. That's a direct solubility. But the thing is that if you are starting, and usually when you are proceeding with a crystallization process, you start with an undersaturated solution. So this solubility is dividing the diagram into 3 phases or 3 places. Below the solubility, that's what we call the undersaturated. So it means that in this case here, you cannot have any crystals of interest that can survive. It's dissolved, and you're going to get a clear solution. On the other hand here, where I put like the primary nucleation zone, it's called also the labile zone. That's where, in fact, you cannot have a clear solution. Here, you will always have a suspension, a slurry. That's, in fact, the domain of the nucleation, and the nucleation is the appearance of crystals. Now, if you want to crystallize, right, in this case here, you have to cool down, but you're not going to get some crystals as soon as you pass the solubility. You need to have a driving force, and the driving force that we have, so if you cool down, the first crystal will appear at this point here, right? And for what we call that supersaturation. So in fact, that's the driving force. The supersaturation is the difference of chemical potential of the molecule in solution at that concentration versus the molecule at equilibrium. And that change, or that difference of chemical potential, drives the molecules in solution to be dissociated, starts to get together to get into a more stable form, which is now the crystalline phase. So when you get there, then that's where you get your first crystals. And as the crystals are nucleating, so they are forming, then they will start to grow as well. And as they grow, nucleate and grow, they will eat or consume the supersaturation. In other terms, it means that the concentration will drop from this concentration, for instance, 160 grams per liter, to the solubility at that temperature. So between the solubility and, so below the solubility, you just have a clear solution. At the solubility, it's an equilibrium, which means that no dissolution occurs and no growth occurs. The crystal is at equilibrium with the solution, in fact, with the solute in the solvent. But in between then that curve, the solubility and the metastable zone, the limit of the metastable zone width, and that's what we call, right? You have a space where you can have a clear solution. And that's the zone where we are sitting. And we are sitting in order to control the form, in order to control the particle size, and also reduce the variability in terms of purity, right? So nucleation, and that's called the metastable zone here. So it means that if you cool down, when you are here at equilibrium, no crystal can appear. There is no driving force. When you are at this stage here, crystals appear instantaneously. In between, the crystals, the solution can stay clear, but as the supersaturation is increasing, as you drop the temperature, for instance, then the induction time, the time for the crystals to appear, is decreasing as well, right? So it means that if you stay at, for instance, at 40 degrees here, you will have like some clear solution, but if you wait long enough, right, depending on the supersaturation and the temperature, which are kinetics, right, then some crystal will start to appear. And then they will try to reach their equilibrium, which is the solubility. So as I said, that's the zone that we are determining in order to do some seeding. Now, what is also interesting is that the trend or the profile of the solubility here in this case it's like increasing. It's a direct solubility. So that's a good solubility in order to do a cooling crystallization. But in fact, the profile of the solubility will in fact drive the type of process that you're going to run. For instance, you have some molecules that they have a reverse solubility, which means that the solubility is decreasing as the temperature is increasing. And that's typically what you see like in your washing machine, that white stuff that you have, or like on your the scale that is forming also on your water tap. In fact, it's because it's insoluble at high temperature, and they are doing what we call heterogeneous nucleation. They are crystallizing on the surface of your tumbler, like of your washing dryer, right? So in this case, if you want to drive the crystallization when you have a reverse solubility, it's not by cooling, but it's by heating the system. Now you can have also some solubility that are very flat and very high. That's typically the solubility of NaCl. And in this case, you're not going to do a cooling crystallization because you're not going to be able to provide enough supersaturation and get enough yield this way. So what you're going to do is that you're going to do some evaporation. And that's typically the way we are processing NaCl, which is the salt table, right? Now, sometimes you can have like solvents where you have very high solubility and another solvent where you have very low solubility. And those two solvents are fully miscible. So that's the kind of combination that we use to do anti-solvent crystallization. And the process is very simple. It's like you dissolve your molecule of interest or your solid of interest in the good solvent, and you use the anti-solvent to decrease the solubility and trigger the supersaturation to drive the crystallization. So from Marseille in 1999, the year after my experience in Lyon, I went to the CRMC2, which is the Centre de Recherche sur les mécanismes de la croissance cristalline, which means the research center for on the mechanism of crystal growth. That was established by Roland Boistel in the 60s, and Roland Boistel was a big guy in crystal growth, nucleation, etc. I was working for Elf Atochem with Stéphane Wessler, who was his PhD student, but since Roland Boistel died in 1998, Stéphane Wessler is heading the lab in Marseille. So it's been like almost 25 years now. So that was my first experience with polymorphism and in fact hydrates, really, in this case. And the point of the work that I was supposed to do, or that I was doing, I did, was to understand the caking issue of perchlorate, of sodium perchlorate, NaClO4. So what is caking? Caking is like as this picture. Can you see the picture? I'm not sure because there is yeah, you can. All right. So caking is basically when you have a loose powder that eventually ends up like with lumps like that on the left-hand side, right? And that can happen for many different reasons. But for this case here that I can detail, and I will detail in the course like in October, but like for this case here, in fact, what happened is like we had a phase transition. So sodium perchlorate, the sodium perchlorate that Atochem was making was a monohydrate, but it also has a dihydrate, which is more stable. So what would happen is this compound is very hygroscopic, the monohydrate. So on storage, what would happen is like it would like pump, depending on the RH, the relative humidity, the hygroscopicity of the air, it will pump some of the water from the air, right, and absorb it. And on the surface of the crystals of the monohydrate, it will start to dissolve. Now you have, and those crystals, like you have one crystals of monohydrate, another one, and then in between, in fact, the surface will dissolve, and then they will be linked with a liquid bridge of those dissolved material. But now this solution here is supersaturated with regards to the dihydrate form. And what would happen is that then the dihydrate would start to crystallize and cement two particles, neighbor particles together to end up like with a clump like that. That's exactly the same process that is used or that is happening when you're doing plaster, and we'll talk about that a bit later. So in 1999, so that's why I started my PhD with Professor Jean-Paul Klein, and it was sponsored by Sanofi Santé Labo at that time. And it was my work was the experimental. I set up an experimental methodology for the screening of polymorphism from solution by direct nucleation of the stable form. And for that purpose, in fact, I took advantage of a phenomenon which is called heterogeneous nucleation, which is basically the crystals, they don't form in the bulk, they form on the foreign surface. And that's heterogeneous nucleation. That's the main mechanism of formation of snowflakes, for instance. So when you have heterogeneous nucleation, what happens is like you reduce the metastable zone width of the different form. And then when you cool down, you might encounter, in fact, the metastable zone width, heterogeneous metastable zone width of the stable form. So that's why, in fact, it will crystallize more likely than the metastable form. And that explains why it's happening also at larger scale, because when you are in an industrial settings, the main mechanism of formation of crystals, it's heterogeneous nucleation. And it's heterogeneous nucleation because you have a lot of dust coming from everywhere, from the air, but also you have a lot of particles that are coming from the upstream, the chemistry. And it can be carbon, black carbon, that is used, in fact, to remove the color or make some adsorption, or it can be remaining silica that was used in the previous step, or it can be platinum, palladium, remaining platinum and palladium, nanoscale platinum and palladium that were used as a catalyst on the previous synthetic step. And those guys, they can act as a surface to accelerate the nucleation of a stable form. So we also did, when I was working there, I was working also in collaboration with Marseille for all the expertise on crystal growth and nucleation. I was working with Dr. Laurent Laferrère on liquid-liquid phase separation, LLPS, which is very similar to crystallization, but the story is that you have a molecule which is dissolved, you create some supersaturation, but instead of having like some crystals, what happens is like you have some oil forming, right? And this oil can crystallize or not. And that's a problem. And that's well known by chemists. And the term that they use is oiling out. That's exactly the same type of process that's working, that's happening, in fact, with this liquor, which is called pastis. Normally, pastis is from Marseille, but I use this one, pastis de Nice. Sounded good. But the idea is that you can see that it's a clear liquor. But as soon as you put like some water into that system, right, it becomes like opaque and turbid, as you can see in the glass here. But in fact, if you look under the microscope, what's happening in that glass here, in fact, you will have a continuous phase and droplets, oil droplets. And what happened is like, in fact, those pastis, it's like arak for Lebanon or ouzo for the Greek, right? They have this smell, which is like anisey smell. So I couldn't find any equivalent in Brazil, but I'll bring you one day. When I get there, Maria. So I couldn't find any, but basically what gives that smell is called transanethol. And transanethol is very soluble in ethanol, but it's insoluble in water. So when you add some water in that, it's like doing an anti-solvent process for this transanethol that in fact eventually phase demix, right? It's called phase demiction or liquid-liquid phase separation. But this happened, and the reason why I'm mentioning that, because it's happening a lot in the pharma industry whenever you develop an anti-solvent crystallization. And for instance, if I give you like this example here, that's the example of ibuprofen, the RS, so the racemic mixture from ethanol water. So if you dissolved your ibuprofen in pure ethanol, and when you add like some water to a point, then you will reach at a given supersaturation, you will reach a point where in fact, instead of crystallizing, you're going to have the formation of oil droplets, as you can see in that video. Hopefully you can see the video, all right? Thumbs up? Yeah? Okay. So in fact, the first step is the formation of these oil droplets. And this happened at what we call the spinode. That's where the demiction is occurring. And then those droplets will reach a critical size. And once they reach that critical size, then they are supersaturated and they can crystallize. Once they crystallize, the droplets, the concentration is changing and we're getting back in a one phase system. So that's why you see that around that crystals, you don't have any droplets. And you can see those guys here, they are disappearing because this crystal is growing and there is a transfer of matter from those highly saturated, supersaturated droplets to those crystals that are growing. And you can see this one here as well is growing. And if you look on the surface of this crystal here, you can see what we call a secondary nuclei as well. So this is done under the microscope, but if it was under agitation, the shear would have break that small crystals and bring another crystal. So that's what we call secondary nucleation. Right, let's move on. No, let's move on. Why is it important to deal with like LLPS? It's because when you're developing a crystallization process, you want to have a robust, you want to ensure quality, which means purity, and you want to control the form, and you want to control the particle size distribution, and you want to have something crystalline for that, right? But whenever you are confronted to this kind of situation, LLPS, you quite often have impurity entrapment. You don't control the physical properties of your API. As you can see here on that picture, what you end up with is like kind of a spherulite, round-shaped crystals, and like small crystals that occurs, in fact, later by secondary nucleation. And sometimes, and this is if you are lucky, you have something crystalline. If not, you often have like something which is sticky and amorphous, and then you fail your batch, and then you have to rework your batch. Not mentioning that on scale up, if everything is stuck, then you can break the agitator arm as well and the motor. So it has a lot of implication there. But during the course, I will show you how to control that, how to understand what's going on, how to control that, how to avoid that, and how to troubleshoot that as well, right? And it will all go through the determination of the phase diagram. Let's move on. So from Lyon, when I finished my PhD, I went to Montpellier, south of France again, very nice, the sea, the Mediterranean. And I worked with Olivier Monnier, and I did a postdoc on supercritical fluid crystallization. That's also the place where I started to learn with Olivier Monnier how to develop crystallization process for scale-up. But just here, I'm just going to illustrate the supercritical fluid. So what is a supercritical fluid? If you have like a pressure temperature diagram, you recognize that three states, solid, liquid, gas. And here you have supercritical. So what happens is like if you start to heat up a solution of carbon dioxide, in this case here, in enclosed, right? So in fact, you will follow that curve here. And as you go, so you can see on this picture that you have two distinct phases, right? You have the liquid carbon dioxide and at equilibrium with the gas, right? As you increase the temperature, in fact, this system starts to expand, and in fact the limit between the liquid and the gas is less and less pronounced until you get to a supercritical fluid, where in fact you just have one single phase. And in fact this phase is very interesting because it is a mixture, not a mixture, but it's in between a liquid in terms of density and solvation properties and a gas in terms of mass transfer. So it means that when we have molecules that are difficult to crystallize with normal solvent, because the mass transfer is so fast in this kind of system, you can get, in fact, crystalline phase where they would be amorphous in a normal liquid system or solvent system. So we use that system, or we use that technology to do some screening of polymorph. Oh, sorry, and I forgot to mention that obviously it's a thermodynamic thing, so it's reversible. So if you cool down the system, you will recover your two phases, right? So how do we use it? So there are two ways of using carbon dioxide. Either the molecule is soluble in carbon dioxide, and then you will use carbon dioxide as a solvent, right? Where you will percolate, and that's typically what they are using, for instance, for cannabis in the cannabis industry. They load the cannabis flower, they percolate with a supercritical fluid carbon dioxide. The THC, CBD, and all the components they are interested in is dissolving into that. It's high pressure. So then the liquid, the supercritical fluid is then pushed forward into a venting system where you drop, in fact, the pressure. Now the carbon dioxide becomes gaseous again, right? And then you will precipitate, or you will drop your whatever that was dissolved in the carbon dioxide. In our case here, we use, because most of the organic compound that we have in the pharmaceutical industry, they are insoluble in carbon dioxide. So in this case, in fact, we use carbon dioxide as an anti-solvent. And the principle is very simple. Once again, you have your drug, which is dissolved in an organic solvent. and then it's mixed with carbon dioxide, supercritical carbon dioxide. And in fact, supercritical carbon dioxide acts as an anti-solvent, and precipitation occurs. And then after, we have a receptacle at the end where you recover the solvent and you vent the carbon dioxide. In fact, the carbon dioxide can be then recycled and then reused in the future, right? If you want to. Hopefully I'm not too long. So we use that for the screening of polymorph, as I say. Like, for instance, in this case here, we were able like to do to deliver like 3 different forms very quickly that were not known, right? And also, by having this kind of information, you can also couple that with DSC and have an understanding of the relative stability using the Berger and Remberger rules in order to understand which one is the most stable, just on the DSC. When I say most stable, it doesn't mean necessarily that's the one which has the higher melting temperature. When we talk about stability from a thermodynamic point of view, it means the one which has the highest enthalpy of melt, not necessarily. So now, if you compare, you can have like some systems, for instance, where like, let's say you have 2 polymorph, right? 2 crystalline phase, right? They have 2 different melting points. If their melting point, if the like form A, for instance, if its melting point and its enthalpy of melting is the highest, you will have a monotropic system. Now, if the one which has the highest enthalpy of melting, so the more stable at 0 Kelvin, right, from a thermodynamic point of view, also has the lowest temperature of melting, you're going to have an anisotropic system. So just by doing some DSC, measuring the enthalpy and measuring the temperature of melt, you should be able to define if your system is monotropic or anisotropic without doing any solubility. So we use that system as well to do some particle engineering. You can get like micro or even nanoscale particles, very small ones. So that's very interesting when you want to improve the dissolution rate and the bioavailability of your compound. We can do also some formation of amorphous compound. Once again, if you have a compound which doesn't have a good solubility or dissolution rate, you turn it into an amorphous compound. And lastly, in fact, we can obtain as well the first crystalline phase very quickly. We have what we call lazy molecules. Typically, they are large molecules with a lot of twisting, and they have a lot of degree of liberty, and they struggle to crystallize. The problem is, like, if you want to go from medicinal research to preclinical and then development, you need to have a crystallization process. At least at Sanofi, that was the case, because there is a kind of a diktat. Because if you have a crystalline phase, it means that you have a way to purify your system. So which means that you can develop your process, chemistry and crystallization without the use of chromatography. Because keep in mind that crystallization is the simplest, most effective, and less costly way of doing purification, right? So that's a very good tool. Maya, you tell me, because I'm already, I think, over the time. Maybe I'm just going to finish that part here, and then I'll leave the rest for tomorrow. If that's okay, right? So I went in Ireland. So just last case, and then I will go very fast for the last 3 slides. So like from Montpellier, I ended up like in Ireland. So it was a big cultural shock, right? Especially because I came like from the pharmaceutical industry where everything is white, south of France, nice weather, and I ended up like in Ireland. And I love Ireland, and I love Irish people. They are great people, good crack, as they say. So I worked in the framework of the Marie Curie European Research Program, which was basically they would take like young researcher, academic, and put them into those big industries to transfer the knowledge. Like in this case, it was the knowledge of crystallization. So this is a very good example of a high tonnage continuous crystallization process. What we are making on this plant, it's called alumina. Alumina is used for ceramic, but also to make aluminum with an electrolytic process. But that's not what we're doing here. What we're doing here is alumina. And how we do alumina is like it starts from bauxite ores, which are rocks, and those rocks comes from New Guinea, Jamaica, Australia, obviously, New Zealand, etc. So those rocks are broken, crushed, and then after they are mixed with caustic soda, NaOH, high concentration solution to dissolve, because in fact the gibbsite Al2O3 is soluble in caustic. Then after, so that's the digester, it works at very high pressure and very high temperature, and then after it's transferred into this kind of decanter. It's where the mud separation, so you separate the rest of the ores, the rocks, from the solution that contains the alumina. So there is some filtration, and then after that, liquid is then transferred into the precipitation, filtration and washing unit, which is here. So you can imagine that, in fact, all of these tanks here, right, these ones here, they are 4,500 meter cube, which is 4.5 million liters. So you can understand that it's not the same scale that we used to have, that I used to have personally in the pharma industry. We used to make 1.8 million tons per year of alumina, right? So, and then when you want to do some piping or some sampling, right? It's not like with your pipette. You go underneath and you go with a hammer in between two rigs and just by the big, how do you call that, pump. And to take like 6 liters of solution, you spill like maybe 40 liters of that. But it's very hot. And obviously it's very dangerous because it's high caustic, right? So you can dissolve your bones as well. If you want to get rid of a body, dump it there. Anyway, but so that's what we make, right? And that's the gibbsite, but the alumina is exactly the same. So there is like, sorry. So what I should say is gibbsite is a dihydrate of alumina. So once we have crystallized the alumina here, the gibbsite, sorry, then after the gibbsite crystals, like this one here, are calcined, so basically heated very high to get rid of the water and then get the alumina. And then after the alumina is charged back on the boat and go wherever it has to go. But what is important in that case here, once again, you were talking, Maria, about particle size, you were talking about polymorph, etc., about CQA, critical quality attributes. The critical quality attributes of the alumina, the end product, is dependent on the crystallization of the gibbsite. And how does it work? This is working on at this stage here. In fact, you have the pregnant liquor, which is coming. They call it pregnant liquor, which is nice, interesting, because it's going to give birth, right? It's going to nucleate. So it goes like through a section of 3 agglomerators where, in fact, and it's a continuous process, right? So you already have like some solids there, right? And each of them, there are 2,500 meter cubes, so 2.5 million liters for each of them. And then that's where the agglomeration, so you have 7.5 hours of residence time along that, right? That's where the agglomerate, the start of the agglomerate is starting. And then after it goes into that section here, which is the growth and the cementation. So that will give the strength of the gibbsite, because what you don't want to end up with a powder or small particles that's going to go like dust and go in the air, right? So you really need to have some specific size. And for those, the alumina, it's 110 micron. So you can see at the end of, so there is a drop of temperature because the solubility is dropping with the temperature here, right? And at the end, so you have some cemented. And then after you have a section of what we call classification, where you separate crystals by their size. And this happens in decanters. So the first part here, which is the big crystals, they go to filtration and wash and the calcination. In fact, after the filtration, they fall onto a belt conveyor that brings them into the calcination. The bigger parts here are in fact recycled at the cementation. They are big, but they are not big enough. So they're going to do another cycle to get to this 110 micron. And the finest crystals here, they are recycled in the first agglomerator here, all right, to restart. And this is a continuous thing. So I'm not going to go into details, but if you look at the mother liquor here, the pregnant liquor, there is a part which is here, right, to start the agglomeration. There is another part which is here, and there is another part here. In fact, it's all to maintain the supersaturation, because what happens is that once you have done the filtration, the liquid is less supersaturated, is less concentrated, right? And in fact, you use that to recreate some supersaturation, because if you can see here on those solubility curve, they are changing with the temperature, but they are also changing with the concentration in caustic as well, right? So from Ireland, I went to Pfizer. So I'm going to go fast so we can stop on time. I worked at Pfizer in Sandwich, where I am, not very far. I worked in the CR&D, which is the chemical research and development. I did some crystallization process development and isolation process scale-up and transfer. So when we talk about isolation, in fact, you have to think about crystallization, filtration, and drying. And I would say also delumping as well at the end, right? So it's the entire section there. So I worked on batch and continuous. Also, I worked a lot in order to maintain the CQA downstream, not only on the crystallization, but more importantly on the dryer, because you can control your crystallization. But if you go to an agitated filter dryer, you can break all your particles or you can boil up. And I will show you example as well if you participate to the course. So I worked at the interface of drug substance, drug product. That's what we do in the pharmaceutical industry. I did some particle engineering, process modeling, because that's the paradigm today. You're trying to do less experiments, right? So you try to extract some kinetics, do some in silico, both for the solubility as well as determining the crystallization kinetics. And once you have the crystallization kinetics, then you can do more modeling and simulation there. I did some solid form screening and I worked from early to stage compound. So from the UK, I went west to the US. So I went to Indianapolis. I worked for Eli Lilly. Well, I'm not going to develop more, but the most important thing here is that that's where my kids were born. And I'm forever attached to Indianapolis, the Midwest. Love it. Very good friends, and my kids are from there. Anyway, a lot of different things, CMC and QBD. I was part of the Enabling Technology Consortium, and I did a lot of different things, whatever. And then from Indianapolis, that was my last assignment. I went to North Chicago, and I worked for AbbVie. I was a technical lead at the Center of Excellence for Isolation and Separation Technologies, the Coexist group, and I did a lot of different things. Yeah.
Can we back for from United States from tomorrow? Can we start from there?
Yeah, okay. That's the last slide, and then tomorrow we'll start with something else. And then in June last year, I went back in the UK, back where I was in Sandwich. So I created that Moussa Boukerche Consulting LLC. So it's an LLC because it's in the US, because I was not allowed to work in the UK while I was waiting for my visa. And I've just also set up and registered INCRIST. It stands for Innovative Crystallization. So that's a lab that's going to be in the ex-Pfizer site. And hopefully it's going to be up and running by end of September, early October. And the purpose of that is to develop crystallization process for customers. And then tomorrow we'll talk about crystals and etc. and everyday life crystals. Sorry, I'm a bit long. Thank you very much. And até amanhã, se Deus quiser. Am I good with that? All right. Thank you very much.
Thank you, Moussa, for the presentation. Very clear. For my part, I could understand everything. It was very clear, very didactic.
Yeah. And I understand. I speak very fast, and English is not my mother tongue, so yeah. I can understand. So that's why I try to put a lot of visuals and stuff to illustrate. But if people have questions right now or later, we can follow up on that. Yeah,
the idea is this. So before we move for the, I will speak in Portuguese, okay, Moussa?
Let's go. I'm working on it, so I'm practicing as well.
Então, gente, eu gostaria de... a próxima etapa agora são as questões, né, sugestões, se vocês tiverem questões a fazerem. Mas antes de a gente passar, eu queria oferecer a vocês o nosso curso, que está com promoção hoje no nosso webinar. Ele vai ficar com desconto de hoje até amanhã. Então, esse curso, né, ele é voltado para a parte de atributos de qualidade, estado, sólido e também a parte de cristalização. Essa parte de cristalização, gente, é uma oportunidade incrível que a gente está tendo com o Moussa participando desse curso. Eu acho que vocês deveriam aproveitar essa oportunidade, porque aqui no Brasil nós ainda temos muita dificuldade com essa parte de processo, e ele se disponibilizou a fornecer esse curso, né, a participar desse curso. Então, eu gostaria de convidar todos vocês a se inscreverem. E aí, tá, os 4 primeiros que se inscreverem no curso vão ganhar 1 hora de consultoria com Moussa, sendo, né, que os 4 primeiros participantes têm que ser de empresas diferentes. E, além disso, os 10 primeiros inscritos, eles vão ganhar também o e-book sobre polimorfismo, um e-book que eu fiz, e que o Nelson, Clara, da Prática na Luz, fez a introdução do livro, tá? A introdução do e-book. É um livro bem didático para quem está aprendendo essa parte inicial sobre polimorfismo. Então, agora eu gostaria de abrir o microfone para vocês. Eu vou deixar aqui todo mundo desmutado. Então, quem quiser pode abrir o microfone. Por favor, só vou pedir, se puderem abrir a câmera. A Cindy colocou o link, tá, gente? Para quem quiser se inscrever. Então, aproveitem essa oportunidade. O desconto vai até amanhã. E aí eu vou abrir aqui o microfone para que vocês possam fazer perguntas. Se quiser também, pode fazer pelo chat, tá, gente? Então, já está aí disponível para quem quiser abrir o microfone e fazer perguntas. Fiquem à vontade. Pergunta, comentários. Então, eu espero que, pelo que eu estou vendo, não tem perguntas, né? Espero, então, que tenha ficado bem claro, que vocês tenham entendido essa parte de atributos de qualidade, também parte de cristalização. Amanhã a gente vai voltar a falar um pouco mais sobre o aspecto dos atributos de qualidade do estado sólido também, como também a parte de cristalização. O webinar, gente, ele é feito para mostrar, trazer um overview, né, sobre o assunto e também mostrar nosso conhecimento. E que vocês possam também identificar se tem afinidade com a gente, nossa forma de ensinar, nossa didática, e que é o que vai ser aplicado ao longo do curso. A gente traz bastante case, né, estudo de caso, para que seja bem aplicado mesmo ao dia a dia da indústria e fazer uma conexão, uma ponte entre a academia e a parte da indústria. Esse é o nosso objetivo. Bom, Moussa, I think no one has questions. What?
I didn't talk. It's not me. Can you hear? It was not me. So someone has a question?
No, I don't think they have.
Okay.
Tem gente que também está sem microfone, né? Mas então, gente, eu espero que vocês tenham aproveitado o nosso webinar, que vocês tenham gostado e aprendido um pouco. Amanhã a gente vai continuar no webinar, no mesmo horário, e a gente volta a trazer outras questões, outros tópicos sobre atributos de qualidade de estado sólido, assim como a parte de cristalização. Eu vou agradecer o Moussa. Moussa, thank you very much for the presentation. It was very clear. Again, thank you again. So I'm telling that tomorrow we are going back to the same discussion about critical quality attributes from solid, critical quality attributes of solid, and as well the crystallization.
Yeah, sounds good.
So if they don't have questions, we can finish. Thank
No questions, good question. That's good. Obrigado a todos. Okay, thank you very much. Okay, I'll see you tomorrow. Same place, same hour, same time, right?
Yes.
Bye-bye.
See you.
Thank you very much for everything. Thank you for the organization. Very well. Well done. Thank you. Bye-bye.
Bye-bye.
Bye.